Okay. Thanks a lot. First of all, thanks for inviting me to Taiwan. It is more than 20 years ago since I last was here, so it's good to be back. Thank you for that. And my topic for today will be perhaps a slightly unusual one. We will see how we can use Python to design digital hardware. Digital hardware design, also known as chip design. So, okay? Okay, yet? Oh, sorry. Okay, that must be better. Should I start again? No? I think that's fine. Okay. So, digital hardware design, also known as chip design, and of course, here in Taiwan is basically a very good place to be for that, that purpose, because you have some great companies and design houses who do that. So I assume that everybody here knows what a chip is. Is there anybody here involved in chip design or production or in that, working in that industry? I see a few hands. Okay, well, this is a chip. So you see, basically it has some pins to the outside world. And this is in fact an image sensor application. So the big part of this chip is not digital at all. It is basically a CMOS analog circuitry that capture an image. The chip also has a digital part, very complex image processing, filtering algorithms, to enhance the quality of the image. And that part, that digital part, is right here. Oh, sorry. Wrong button. Here, that small black blob over there, that's a digital. So you see, you work very hard for months and months, and then it ends up being something tiny like that. It's amazing sometimes. Here's another chip. Again, it's a sensor application chip. And also here you have these structures here are not digital, but they are analog. Sensor chips are typically mixed signal, analog and digital. And here you have an area which is typically for a digital part. You see routing channels and routing go all over the place. So this is the digital macro for this chip. Now, why did I show you these chips? There is something special about them. One thing is, I was the designer for the digital part. That may not be that special, but the real interesting part is, it was done in Python. So unlike the mainstream design flows, the whole behavior of the digital part was described in Python. And then there is a whole automated flow that takes this Python code down to an implementation. And it was done using the MyHDL library that I developed. So that will be my purpose of today, to show you how I designed this MyHDL library so that you can do this kind of stuff. Let's first discuss how mainstream digital design works. In fact, it is language-based. In the industry today, people use languages to design digital hardware. Such languages have a special name. They are called a hardware description language. Okay? And the industry standards are Fairlock and VHDL. Does that ring a bell? Is there anybody here who has used or who knows Fairlock? Ah, more hands. Very good. Anybody uses VHDL? Also, okay. So these are basically the industry standard languages to do this. So now the question is, why do we use special languages? What makes an HDL special? In other words, what is the difference between an HDL and a general purpose language? One possible answer is this one. The difference is 4,317 lines of Python code. Because that's exactly the line count of the MyHDL library. So this is just to tell you how much effort or few effort it takes to turn Python in such a HDL. Of course, this is rather a joke. We want a clearer answer. So let's investigate what an HDL really should do. And to do that, I will first present a very simple model of a digital hardware system. So what you see here are all kinds of blue rectangles, and they represent small threads, small execution units, threads. And then you see these red arrows, and they represent communication between these threads. In hardware design, we call these signals. So these red arrows represent signals between threads. And here in the bottom, you see a special signal, input signal, which is basically going up and down all the time and that goes all over the place. That would be the clock signal. Very typical in hardware design. So, now what does this mean? It means that digital hardware contains a massive amount of concurrent threads. Concurrency. It has concurrency. The communication occurs through signals, and then on these signals, value changes can occur which trigger events between the threads. And then another very important thing is that as we have concurrency, we have the problem of determinism. So, as you know, whenever you design a concurrent system, you have to take care that it is deterministic. And in a hardware system, we cannot afford to think about every problem, concurrency problem that we can have. We want to have a built-in system, something that always works. That's how hardware works. And of course, an HDL needs that also. And then a final characteristic is that we want to use fine-grained control of bit width. We don't want to use 8 bits or 16 or 32 for every variable. That would be a waste of resources. So we want to control the bit width in a fine-grained way. So here we have a set of requirements that an HDL must support. So a way to view an HDL is as follows. It is an event-driven micro-thread programming language with built-in determinism. That's my definition. And it needs a hardware-friendly type system. Now, I have to warn you about something. This vision suggests that digital hardware design is a kind of programming. Because event-driven micro-thread programming is those words we know from other areas, especially in the Python world, in fact. So that's how I view it, as a specific type of programming. But if you tell this to a die-hard hardware designer, he may not like it. He may think he's special and that he's doing totally something else. So one of the things that MyHDL tries to prove is that that is wrong. That actually it is, if it's not programming, then it really looks a lot like it, okay? So to design this library, we need to support the following features. We need micro-threads, we need events that trigger actions, we need determinism built in, and we need a type system that is hardware friendly. Okay. I will start with determinism. How do we do determinism in an HDL? The trick is to have separate phases for value updates and computations. What you see here in the red circles are value updates, and in the squares, blue squares, you have computations. And these occur in phases. So first value updates, computations, etc. And by ordering in that way, you can prove that, or you can see, that you will never have the situation where some value sneaks in somewhere here and starts, and so that the outcome starts to depend on the order of the computations. So this is in fact how hardware itself also works. If some of you know how a flip-flop works, with a flip-flop it's like that. First you set up all the input values, and then you have a clock signal, and then the inputs are transferred to the outputs. So you have these separate phases. So that's how we do determinism. So the first class in MyHDL that is important to know about is the signal class. Because that's in fact what I call the leaf object of determinism. What a signal does, it buffers the value. It's not like a variable that immediately transports the value. If you declare a signal, you can afterwards assign to an attribute, which is called the next attribute, and that means the next value of the signal should be such and such. So all you do when you write MyHDL code with signals is assigning to this next attribute. The updates themselves are not done by the designer, but by a scheduler that runs on top of all this. So they occur automatically. This scheduler, by the way, is called the simulator. And everybody here who has done hardware design will be familiar with that word, simulator. Fairlock simulator, VHDL simulator. So the point is, if all communication goes through signals, then automatically the model is deterministic, and we don't have to worry about it anymore. So this is how this works. Signals also can be used to define events. Because you can have a micro thread somewhere that is waiting on a value change of a signal. It can be just a value change, or it can be waiting for a certain transition, a rising edge or a negative edge on a signal. And very often, there is this one signal which I talked about earlier, which is a globally synchronizing edge, and that's what we call the clock in digital hardware. And that's basically what is called synchronous design, if everything is triggered by a global clock event. And of course, you can define other events. For example, you can define a delay, so you wait until a delay expires, and only then you continue with some further computation. Okay, now, we have covered signals, we have covered events. What about those micro threads? We need massive concurrency in hardware. So, the implementation of this thread should be super lightweight. Cannot use operating system threads, or it has to be very lightweight, without overhead. It has to be as lightweight almost as a function. So, if that's true, then let's just use a function. In MyHDL, the micro threads are implemented by generator functions and generators. If you recall from David Beasley's talk this morning, he mentioned that he thought generators were the greatest thing that was recently, in fact, not that recently, that was introduced in Python. And I agree, because without generators, I wouldn't have been able to do this. The generators are the key building block of MyHDL models. So, what we do in MyHDL, we write generators. They are generated from generator functions. So, for example, here we have a generator function, and you have a few signals, Z, E, B, cell, which are defined in an outer scope, because we use generators in a nested way in MyHDL. So this generator function doesn't have parameters. And here you see a while true loop, which is very common in a generator function because it has to continue to work all the time. And here you see this yield statement. This is what makes a function into a generator function, right? A yield statement is different from a return because after a yield, the function doesn't go away. It stays there, it knows where it stopped. Is everybody here familiar with generators and generator functions, or is that still new? Can you, are you using that, generators? Few people. Okay. So you really have to think about the generator function as a function that recalls a state where it returned. That is all. That is the function of the yield statement. So in MyHDL, what you do is you yield, for example, here you yield a number of signals, and what that means is that you wait until a value changes on these signals. So that's how we implement waiting on events. Okay? So this is basically the global concept. Now, we use generators for all the time, and sometimes, or often, most of the time, it's more convenient to write them in a slightly less verbose way. For example, this is a generator function, but in fact what we need is a generator, and a generator is made by calling such a function. And that would be a little bit, that would be an overhead having to do that all the time. So what we do in MyHDL is we define decorators to make it easier to create interesting generators. Now I'm using a lot of words at the same time. Who is using decorators here in Python? Okay, not that many people. A decorator is in fact a way to modify the behavior of the function that follows. So, what is, for example, what this instance decorator does, all it does is in fact it calls this generator function and then assigns it to the same name, so that we reuse the name of the function as the generator itself. Okay? This is just a convenience thing. Otherwise, we would have to make this call explicitly here. Now, what we have in MyHDL is that we go steps further to make it easier for hardware designers to model things that they are interested in. For example, this while true loop, you have that all the time. So that seems like overhead. This pattern here from while true and waiting on a number of signals is so common that we defined a special decorator for that purpose, and that is called the always decorator. So it does the same thing as the previous generator, but thanks to this always decorator, we have to write less code. We have the inputs here as parameters, and then we have this mux function. But the meaning of all this is that whenever one of these inputs changes, this function will be called. So there is some magic involved here to have the behavior that we want. And we go even further in MyHDL because it is very common that a function should be sensitive to all its inputs. So here, for example, you see that you have the always comp decorator, and you no longer have a parameter list with signals. What this does is it automatically infers which signals are the inputs here, cell A and B, and automatically makes this function sensitive to those changes. So even more magic here. This always comp decorator actually uses the AST parser and a whole compile step to make this possible. Now, why I'm saying all this, this is just because these type of patterns are so common in hardware design that they deserve special support. It's really not feature creep or something. This is used all the time. And I have one more, which is the always sec decorator. This is in fact a decorator that automatically infers the reset behavior. When you use this decorator, then when you have a reset signal, this will also automatically be, sorry, this not it. When you have a reset signal and you use this decorator, then the hardware reset function will automatically be called just because this decorator infers all this behavior. In fact, if you look at this code, it is exactly equivalent to the one that follows here. You see that you just have to write less code because all this red code is no longer necessary. This may sound a little bit specialized, but I'm saying this because this is a unique feature of MyHDL. No other HDL has this type of thing. And this is so common in hardware design that it saves a lot of time. So, the reason why I went in all these details of these decorators is to give you the message that decorators are in fact a great tool to create a domain-specific language, which MyHDL in fact is. So they are really building blocks that create these little languages within Python that do the things that you want. I repeat all these decorators here, instance, always, always comp, always sec. All of these have their purposes. They're not there just because someone asked for it. They are all heavily used. But of course, as I told you, maybe you will think that all these decorators, if you're not familiar with it, that this is feature creep or something. This is not the case, and that is why I have this slide, which tells you that MyHDL really is a minimalistic design. I try to design only the things that are really necessary for the purpose. And I use native Python features as much as possible. For example, to describe a random access memory, I don't invent OR classes or don't use anything special. I just use Python lists. Likewise, to describe read-only memory, I use tuples. These have a similar semantic meaning. Furthermore, for a hardware module itself, there's nothing special in MyHDL. You just use a normal function. A normal function is used to describe a hardware module. The only special thing is that it creates generators and that it returns them. That is the way that hardware is described. To model hierarchy, all you do is call another function. So no special features needed for that. And I have a schematic overview here. So this is basically how a module in MyHDL would look like, including hierarchy. So you have a normal function with a parameter lists, typically all signals. Then you have some internal signals who are defined here. Then you have a submodule, which is just another function call, which is assigned to a variable. We call this instantiation in hardware design. Then you can have any number of additional instantiations or decorators, and all these things are returned. So what this does, in fact, it creates a hierarchical nested list of generators. That is the basic data structure that how MyHDL represents a hardware design as a nested list of generators. Okay? Now, enough about these generators. Let's go to the type system. The type system in a hardware system, hardware design is still typically based on integer arithmetic. For efficiency reasons, that is really the basis of everything. Now, in addition, we have to control the bit widths very precisely. For the reasons that I have told you before, we don't want to waste resources. Now, as this is so important, one would think that any HDL supports this in a very good way. So, we'll see. This is a puzzle, okay? So, here's a variable A in a Python range from 0 to 8, another variable B in the range -8 to 8. The question, calculate C equals A plus B. For example, 7 plus -2 is how much? Any guesses? No. This is obvious, of course. So let's see what Fairlock, the most used HDL in the world, tells you what the answer is. If you describe this in Fairlock, you use signs and unsigns. It goes more or less like this, with the correct bit widths. Here is the equation. Answer, 7 plus -2 is -11. If you don't believe me, grab a Fairlock simulator, try it out, and you will see it's -11. And Fairlock designers will tell you that it's the right answer, because that's how Fairlock works. Anyway, let's look at VHDL. Same thing. Slightly different syntax, but again, unsigned and signs. Equation. Compilation error. You're not allowed to add a possibly negative number to a positive number. Doesn't work. So, what's the problem with all this? The problem is that Fairlock and VHDL use lower level types. They come from C or so originally, I guess. Non-abstract types, signed and unsigned, which basically are very close to the representation. And in both cases, mixed expressions are problematic. Fairlock, for example, casts everything to unsigned in a mixed expression. If you mix signed and unsigned, it casts everything to unsigned, which is the opposite of what you should do. And in VHDL, you have a strongly typed language, which is fine by me, but strong typing really doesn't work well with this kind of lower level types. It just makes life more difficult. So, what I guess I want to say, with MyHDL, of course, I want an HDL based on Python, and I want all these goodies that Python provides, but I also try to make a better HDL. Why not? While I'm at it. Huh? So, in MyHDL, we just use integers. You know, in Python, we used to have the difference between a normal int and a long. Fortunately, that's gone already. Also now, you just have integers. And they can be negative or positive, whatever. So in MyHDL, we do the same, but there is a specific class so that you can constrain the values of the integer to a range. You see here, for example, A is sorry, let me go back. The integer class that does the integer-like class that does this is called int_bv, for integer with bit vector capabilities. So, what you can do is specify a range, like here. You specify the minimum value, the maximum value. And this is very interesting, because in fact such a range gives you free assertions. If you write a model with MyHDL, and for some reason you have a problem with your model so that the values are exceeded here, you get an exception, a traceback. So there is no rollover like with, for example, with signed and unsigned types in hardware decryption languages. It tells you where the error is. At the same time, these bounds, of course, can be used to minimize the bit width or to specify what bit width you need. So you have two purposes, a low level and a high level purpose with one feature. And of course, this is hardware, so we need to access the bits. That's why this int_bv class also has a slicing and an indexing interface. So you can access the bits that you want from a specific slice or index, and you can set them. So this is, in contrast to the Python int, this is a mutable class. Okay. This is basically the workhorse, let's say, together with the signal type of MyHDL. Right. Now I have to make a small side note and tell you about synthesis. Because in hardware design, we don't have just one compiler, we have two compilers. We have one that we use to compile to a simulation database so that we can simulate and verify the design. And then we have another very important compiler, which is called a synthesis tool. Synthesis tool is a compiler that compiles an HDL design into a gate implementation. Is anybody here familiar with synthesis? Few people? Is Young Yu here? Hi. What? Not from that. But you worked at Synopsys, right? Okay. Synthesis is very important in the hardware design world. There was a company, there is a company called Synopsys that became big based on this. Synopsys, in the beginning of, in the early years, the tagline of Synopsys was the synthesis company. So this technology is very important because it basically enabled language-based design for hardware designs. Now, synthesis, unfortunately, is rather restricted in the sense that you have to write your HDL in a very specific way to get it through the synthesizer. Fairly low level, actually. I wouldn't say that it's like assembler, but it's fairly low level. And that level is in fact called the register transfer level. So when a hardware designer tells you that this model is at the register transfer level, the RTL level, then what this means that this model is intended to be synthesized, to go to hardware directly. Okay? Now, synthesis is available for multiple vendors. From FPGA vendors, EDA vendors, and in all kinds of price ranges. Free, and also very expensive and very good. But, as you can imagine, it's Fairlock and VHDL only. So you see the problem with MyHDL. I can have a very good HDL, perhaps, but if I don't have a link to synthesis, I don't have anything. Anything practical. So, for that reason, MyHDL contains a converter. A subset of MyHDL can be automatically converted to Fairlock and VHDL. This is not really in itself a synthesis tool in the sense that it maintains the abstraction level. There's no change in the abstraction level. However, it supports all these nice MyHDL features which are not in Fairlock and VHDL, so that it automates some tedious tasks and it supports those unique features. And also, I try very hard to make it integrate seamlessly in existing design flows. Because of course, hardware design teams are rather conservative. Well, not of course, they are rather conservative and that's understandable. So I want to make it such that you can basically use MyHDL on a module, try it out on something, and that the output is as good as better or better than what you would have done by hand. And actually, I know just recently someone who was learning Fairlock told me that he found it easier to write MyHDL first and then look at the Fairlock output to learn how Fairlock works, which is true, I think, but also a nice compliment. The important thing here is that conversion is not restricting you for implementation, because what you can convert is much broader than that synthesizable subset that I told you about. You can do much more than just the RTL level, okay? So basically, this is the way that MyHDL connects to the real world. When I told you that it had 4,000 and that much lines, I didn't include this. Because conversion is like a workaround. If there would be a synthesis tool that accepts MyHDL, I wouldn't need it. But even then, it takes up a lot of effort. It's probably the most complicated part of MyHDL, and much more lines than those 4,000 that I told you about. And also, at some point, initially I used the compiler package in Python. I don't know if you have heard about that. And then at a certain point that was deprecated, so I had to rewrite all my code to use the new AST package. And that is really a lot of work, which is why I'm worried about Python 3 a little bit. But that's another subject. Okay, let me give an example of what conversion can do for you. It can do a lot of things. I cannot tell it in the full generality, but just an idea. If we go back to our puzzle, where we add two numbers, then here is how it would look in MyHDL. You have a few signals with the correct ranges, and then you say C.next is A plus B. Okay? In MyHDL, of course, this works as expected. The answer would be, like you had said, 5. 7 plus minus 2 is 5. Moreover, if you convert it to Fairlock and VHDL, the converter takes care of all these little details like casting and sign extension and resizing, all of these things that the tool can do much better than you yourself. So in this way, the answer would match what you really want, which is a simple addition. Okay? So the converter does all the casts and resizing so you don't have to. And it has support for many other things that, in my opinion, make the life of the hardware designer easier. Okay. We have talked about modeling with all these decorator stuff and hierarchy and signal and in BV. We have also talked about synthesis and the backend and that it's all automated, so we don't worry about it anymore. But here is an important part that we haven't talked about it yet. Verification. The reason that I didn't mention it yet is not because it's not important, it's actually the most important thing of everything. That's why I keep it until now. So, but let's first discuss a little bit this design flow. So what you have here, if you have a modeling phase where you write your code, and then you have verification with test benches and all kind of stuff, and you iterate until everything works. This is like you would do in software, right? After that, when you're finished, you convert the RTL code, and you go to synthesis, place and route, and etc. Okay? So this is globally how you design a hardware system in MyHDL. Now, let's talk about verification in more detail now. I think verification is actually MyHDL's strongest point. That's why I did it. Because verification is also, like in software, the hardest part of everything. Designing something, writing some code is actually not necessarily that hard, but making sure it always works under all conditions is very hard. And in hardware design, if you invest a few $1 million in a chip, then making errors is extremely expensive. So what you have with MyHDL is that for verification, There are no limits at all. There is no RTL level. You can use any trick in the Python book to build your verification environment. That's fantastic. That is something that in Fairlock and VHDL you can only dream of. So a hardware verification engineer directly benefits from Python's expressive power and also from the ecosystem, meaning the standard library, the third-party libraries, all the methodologies, the Python conferences, all the work that is going on and that you can use for the benefit of your project. One thing, for example, is that it allows you to do is like agile hardware design. Nobody in the hardware design world has heard about that yet. Well, nobody, that's too much, but they use other kind of techniques for verification and development, also powerful, but I think it's just a shame that they're not aware of what is available in the software world. With MyHDL, you can do that. You can do test-driven design for hardware. You can use unit tests and you can use PyTest and other frameworks to build your verification environment, unit tests and regression test suites. So this is really, to me, this is the main point, the basic idea. That's the fact that MyHDL is a Python library and not a separate language is what enables all this. That's the important design decision that I made. Now, the foundation of all this is an event-driven simulator in the MyHDL library. And I will briefly discuss it. So the simulator, this is a very broad overview. What it does, it takes a hierarchical list of generators. You know, I told you the basic data structure is a hierarchical list of generators. That's the input. And these generators, they communicate through these signals. Okay? So what happens is that the simulator updates the signal values. Based on those values, it checks which generators become active. In other words, which generators were waiting for changes on these signals. And then it runs these generators in any order. Again, the order is not important because determinism is built in, right? That's what it does. That's what the simulator basically does, not more than that. To debug such a simulation environment, you can use classical Python debugging, and again, you can use any Python trick or library to build your environment, but I also added something which is typical for hardware debugging, which is waveform viewing. If you run a simulation, you can ask it to dump a waveform file, which you can then load in a tool, and then you see waveforms like this. Some hardware designers do nothing else, it seems, sometimes than staring at these kind of things. Now, by the way, waveform viewing is a very important tool. It's a very important tool, but it's overrated. It is very good for debugging, for finding the initial errors, to see whether everything works more or less. But it is not adequate for true verification. For true verification, you have to build self-checking test environments. So thinking that you can debug a hardware system and get it error-free by just staring at this is really not okay. Now, just to show you how great the Python ecosystem sometimes can be, I want to talk about PiPI briefly. Anybody familiar with PiPI? Nobody? PiPI? Okay. Well, you should look into it because PiPI, well, you can say a lot about it, but and it's perhaps not always applicable, but basically it's a different Python interpreter, a compliant other implementation. And the interesting thing is that it has just-in-time technology. So it speeds up your running programs by very clever techniques that I don't understand. The point is, the combination of this with PiPI, with MyHDL, sorry, turned out to be great. I have benchmark simulations to test it out, and they're an 8 to 20 times faster overnight. I didn't have to do anything. Of course, these PiPI guys had to work very hard, but I didn't have to do anything, and I got this result overnight. That is fantastic. Okay? With this, just by using a different interpreter, my simulations now are in the range of commercial Fairlock and VHDL simulators, which is a rather remarkable result if you think about it. So this was really an overnight game changer, I believe, basically for free. I use it all the time now for lengthy simulations because it makes a real difference. So that was PiPI. Okay, I'm almost at the end of the talk, so let me briefly tell you what I'm thinking about for the near future. I would like to have some kind of fixed point package natively support in the converter, because fixed point is actually also very useful, of course, but the support at this moment in Fairlock and VHDL is not really adequate, so I think we can do better. I have to do some better, some more support for example, for attribute lookup in the converter to support interfaces in a better way. And of course, Python 3.0. But as I told you, that will be a very gradual process because especially in the converter part of MyHDL, it uses the AST. So this is, of course, again, subtly different. So that will be not straightforward. Initially, I hoped, of course, to find some way, gradually, to have a code base that would work both in Python 2 and Python 3. And I will start to make changes so that it moves as much as possible in that direction. But unfortunately, that's the goal of having a unique code base will not be possible. So it will be a gradual process. Okay. One final slide, of course. If you want to know more about MyHDL, go to myhdl.org. That is your basic gateway for everything you want to know. Manual examples, download instructions, installation instructions, a mailing list, news group, success stories, because MyHDL has been used and is being used also for high volume productions. It is not yet a game changer in the world, but it really works, and there are some very nice projects that have been completed. There is a Twitter account that you can follow. And if you want to see how development goes, it is on Bitbucket with Mercurial. Okay? So, right? Thank you. Thanks for having me here. And I'll be glad to answer some questions.
Hello. We know that IC industry is moving towards object-oriented, like System C or System Fairlock. Do you plan to add, because Python is actually object-oriented programming language, do you plan to add this kind of stuff into MyHDL?
Well, it's there. It's there. Because MyHDL is just a Python library. If you want to use object-oriented features, also in combination with the decorator, you can use these decorators on methods also. That's what I wanted to say. I have added features that are really necessary, but for the rest, it's minimalistic. So for modeling purposes, you're basically unrestricted. The big problem is that you have to make a distinction between MyHDL, the modeling language, which is very generic, and MyHDL, the convertible subset. Because what you can convert and synthesize is always very limited, because synthesis is like that. But as a modeling language for verification for high-level modeling, there are basically very few restrictions, including anything what you want to do with object-oriented modeling. No problem. There are examples of that in the manual, if you want.
Thank you.
Okay, please.
Yeah, so you have a converter.
Yes?
How about, can you make a synthesizer? I mean, the compiler.
No.
Why not?
Well, maybe I could, but no. Look, one reason to use Python as a basis for this project is, of course, that you get lots of things that you need in an HDL anyway for free. This is possible for one person with my programming capabilities, I will tell it like that. Making a synthesis tool is something of a different nature, I believe. I will not even attempt it, I think. Well, not because it's not interesting, but there are so many other interesting things which are, in my view, maybe higher value. But let's wait a moment. With synthesis, if you mean an RTL synthesis tool, like the one I was describing, then that's what I meant now. Higher level synthesis, that's something else. I've been thinking a lot about that. Something that doesn't exist yet, and that would provide a technical added value to hardware designers, so that they could do something with this software that they cannot even do with Fairlock and VHDL. I've been thinking about those kind of possibilities, but nothing clear yet.
Thank you.
Okay. Any other question here, please?
Hi. Usually we will use some library like SRAM from Foundry, to simulation with our Verilog code. So how could MyHDL deal with that? Okay.
So the way that we support this kind of problem, where you have the question is, suppose you have a model from a foundry which is provided to you and which you should co-simulate with the rest. Okay. The whole goal of MyHDL is to try to think at a higher abstraction level as much as possible. Typically, for such a model, it is possible to write a very simple behavioral model instead of it. So in a MyHDL simulation, you would use your own model of what it is supposed to do. But when you instantiate it, you can use what is called user-defined code and call the Verilog macro instead. So that when you convert, you actually get the instantiation of that specific, technology-specific SRAM. See?
So the other question is your table example including multiple clock domain in digital design area. Sorry. Usually we will, for power consumption or some request, we may implement different clock domain in this digital design.
In this talk, I try to make things not too complicated. So I talked about one clock domain just because that's the concept. But there is nothing in MyHDL, like in Verilog and VHDL, that prevents you from using any kind of, any number of clock domains in just the same way. So it's just the same thing. It's an event-driven language. So if you have multiple clocks next to each other, just model them and use them in your models. No problem.
Okay. So in your imagination, we can development with Python's library and MyHDL. Then we simulate with the Verilog will generate before we tap out or.
That's not in my imagination. That's reality.
Okay.
I have done it. So you can indeed you can use this whole flow to implement and verify your whole design in MyHDL, and then only to go to implementation, go to Fairlock or VHDL and basically use them as a backend language. They're good as backend languages, that's not a problem.
Any other questions?
All right.
Okay. Let's thank
Thank
Jan
you.
again. Thank you.